Have you noticed this strange moment with your bank card? You are typing your card number into the form on a checkout page, and at the moment you enter the last digit, a red line appears saying "invalid card number," because your fat finger is 6 instead of 5 somewhere in the middle. You may be thinking, well, it's the bank or payments provider that checked my card number, but actually it's not. It was a piece of mathematics from 1954. The math is called the Luhn Algorithm. That algorithm now runs on almost every checkout page, almost every card terminal, every SIM card and every mobile phone identifier. And likely you've never even heard about its creator, who by the way also created a mechanical cocktail recipe machine. So what math is hiding inside your card number? What is the Luhn algorithm? What does it actually protect you from? Who is its genius creator and how simplicity conquered the world? This is Vital Math. Here we explore and enjoy the beauty of mathematics. Luhn algorithm. Let's go! Look at your credit or debit card. Most cards have a 16-digit number, printed in 4 groups of 4. These numbers look random, but actually they're not. The first digit identifies the network. A 4 means Visa, a 5 means Mastercard, a 3 means American Express or Diners Club. That single digit tells any terminal in the world which company will eventually settle the payment. The next 7 digits identify the bank that issued the card. Together, they call the issue identification number. The next 7 digits are your account number, or, to be precise, the unique identifier your bank assigned the day they printed the plastic. And then there is the 16th digit, the last one. That digit is not assigned by anyone, it is computed. It is a check digit. The procedure that computes it is called the Luhn algorithm. The only job of that check digit is to catch typos in the first 15 digits by applying a simple mathematical test. But what is this test, and how can a string of digits prove itself? Take any 16-digit card number. Let's use this one, a sequence I picked because it happens to pass. And let's apply a simple 4-step procedure. Step 1. Double every second digit. Starting from the right, leave the last digit alone and double every second digit, moving right to left. Step 2. Anytime the doubling produces a number larger than 9, add its 2 digits together. So for example, doubling 5 gives 10. The digit sum of 1 and 0 is 1. Doubling 9 gives 18. The digit sum is 9. The resulting number always stays inside the range 0 to 9. Step 3. Add everything up. The double digits, the untouched digits, and the check digit at the end. All of them into one sum. In our case, the result is 80. And finally, step 4. Divide that sum by 10 and look at the remainder. If the remainder is 0, the number is valid. If not, it isn't. In our case, it's obviously divisible by 10, so the number is a valid card number. That's it. This is the whole algorithm. Walk left, double down every second digit, collapse 2-digit results by summing them, total it up, and check that the sum ends in 0. Because of that last property, Luhn's procedure is also called the Mod 10 algorithm. Simple and efficient. And that is what most of checkout pages are doing when you type your card number. But what does it really protect you from? Simply put, it's foolproofing. The procedure can catch some obvious mistakes that we humans make when writing down or typing a long number. Statistically, 2 errors dominate. The first one is substitution of 1 digit for another, say 5 instead of 6. And the second is transposing 2 adjacent digits, for example typing 55 instead of 25. Together, those 2 account for nearly 90% of numeric transcription errors according to quite an outdated study of Dutch postal data. But what can the Luhn algorithm actually catch? The Luhn algorithm can catch every single digit substitution, 100%. Change any digit anywhere, and the sum changes by an amount that cannot equal 10. The check breaks. It catches almost every adjacent transposition, with one exception. A 09 flipped to 90 produces the same sum, and the algorithm can give a valid output even for a typo in digits. Luhn also catches almost all twin error mistakes, when you hit the wrong key twice in a row. Although there are 3 blind spots, 22 flipping to 55, 33 to 66 and 44 to 77. But Luhn is useless against double errors. If you make 2 typos in the same card number, roughly 1 in 10 times, the 2 mistakes cancel each other out. The algorithm can only see whether the final sum is divisible by 10. It can't tell the difference between no errors and errors that happen to balance. Luhn catches 100% of single-digit substitutions. It catches almost every adjacent transposition except 09 flipping to 90. It catches most twin arrows except 22, 33, and 44 flipping to 55, 66, and 77 respectively. But it's mostly blind to multi-digit arrows, where one mistake can balance another. But why does it work at all? And why these 4 specific steps? Intuitively, the algorithm directly follows from our objective. We want to catch the 2 most common typos, single-digit substitutions and adjacent transpositions, and do it efficiently. That's all we need. Now let's simply convert it into math. Let's start with efficiency. Check digits have only a technical role, the check itself. So for efficiency, we want to minimize the number of check digits, and the minimum is just 1. A single decimal digit has 10 possible values, 0 through 9. So whatever total value we compute over the rest of the digits has to be compressed into that range. The way to do that is using modulo 10. And the main question becomes, how does each digit contribute to the sum modulo 10? The beauty is in how that contribution is defined. And this is where the other objectives come into play. To catch transpositions, neighbors must contribute differently. If 2 adjacent positions add the same weight to the sum, swapping them changes nothing. So we weigh every second digit differently, and the simplest choice is to double it. To catch substitutions, different digits in the same position must contribute differently. For the untouched digits, this is automatic. Change the digit and the contribution changes. But for the double digits, modulo 10 breaks it. Look, 0 doubled is 0, 5 doubled is 10, modulo 10 also 0. So a 0 and a 5 in a double position contribute the same thing. 1 and 6 both result in 2, 2 and 7, 3 and 8, 4 and 9, 5 pairs of digits all colliding. Half the substitutions in double positions would vanish. The fix for this is to sum the 2 digits of the result, or equivalently subtract 9. 16 becomes 7, 18 becomes 9, 10 becomes 1, all collisions disappear. And that's it. From our initial objective, we get the entire 4-step procedure. The algorithm works mathematically, but you can probably feel that it's a very engineering kind of solution, maximizing for simplicity at every step. And you might be asking yourself a few questions now. Why doubling and not tripling? Tripling would also catch substitutions, and it doesn't even need the repair step. And what was the algorithm built for back in 1954, long before the internet and the rise of e-commerce? The answers become clear once you see who created the algorithm. Hans Peter Luhn was born in Germany in 1896. His father ran a printing business, and the plan was for Hans to take it over. The First World War interrupted the plan. Luhn served in the German army as communications officer through the war, thinking about how messages move and how they break. After the war, he didn't go back to printing. Luhn went into textiles, and the work took him to the United States. By the late 1920s, he was an engineering consultant in New York, and he had already invented the first thing he would be remembered for – the Luhnometer. A thin sheet of clear plastic that, laid across a piece of fabric, produces a moire pattern and gives you the thread count. And it's actually still in use today. Luhn kept filing patents. A relay-based calculating machine that added and subtracted in binary. A rotary switch built from metal sprayed onto plastic. The grandfather of the printed circuit boards inside every phone and laptop today. A distributor with numbers hardwired into its circuitry. An early read-only memory. The same idea now lives in chips from your car or microwave. A binary counter that reads punched cards and accumulated totals. And in 1933 he even filed a patent for a mechanical cocktail oracle, a machine that told you what drinks you could mix from the bottles on your shelf. An early recommendation engine 70 years before Netflix. In 1941 Luhn joined IBM as a senior research engineer and continued his innovations there. He was one of the first to use the term business intelligence and also pioneered the hash function, the same technique that decades later would secure every password on the internet and run the crypto industry. The patent for the Luhn algorithm was filed in January 1954, titled Computer for Verifying Numbers. It was not for software, there was no software industry in 1954. The patent was for a small mechanical device hand-cranked that a bank clerk could carry in a pocket. You would key in a long identification number on its dials, turn the crank, and the machine would tell whether the number was internally consistent. This was the problem Luhn was trying to solve. By the early 1950s, American banks were drowning in numbers. Account numbers, loan numbers, new credit card numbers that companies like Diners Club had started issuing. Every transcription was a chance to flip two digits or turn a 7 into a 4. And every such error meant a transaction posted to the wrong account, a payment lost, a customer's afternoon spent on the phone with the bank. Luhn was not trying to stop fraud. He was trying to stop the bank from spending days chasing its own typos. That is how the device was born and the algorithm with it. But the handheld computer itself was never a mass product. By the time the patent was granted in 1960, the same calculations could be done faster on the new electronic computers IBM was selling. But the procedure outlived the hardware. In the 1960s, card networks started using Luhn's algorithm. And in the meantime, as always happens with algorithms, better ones started to appear. But how did Luhn's algorithm manage to conquer the world? In 1969, 15 years after Luhn filed his patent, the Dutch mathematician Jacobus Verhoeff published a stronger check-digit algorithm. Verhoeff catches everything Luhn catches, plus every case Luhn misses, every adjacent transposition and every twin arrow. How? Luhn's blind spots all come from the same source – modular 10 arithmetic. It is what mathematicians call commutative. The order in which each digit contributes doesn't matter. 2 plus 7 equals 7 plus 2. And that symmetry is exactly where certain swaps go unnoticed. Verhoeff solved this by using different math. Instead of modular 10 arithmetic, he built his algorithm on the symmetries of a regular pentagon. And it's actually easier than it sounds. Imagine a regular pentagon. What can you do with it without changing how it looks? You can rotate it 5 times by the same angle, and you can flip it across different axes, also 5 times. So there are exactly 10 moves that preserve the pentagon, 5 rotations and 5 flips. Number them 0 through 9 and you have a new way to represent numbers. Each digit is now a pentagon move. To combine two digits, say 3 and 7, you take the move for the first digit, then the move for the second, and perform them one after the other. The answer is the new state where pentagon ends up. That is the new arithmetic. With ordinary addition, 2 plus 7 and 7 plus 2 give the same answer. With pentagon moves, they do not. Flip the pentagon and then rotate it, and you land in one position. Rotate first and then flip, and you land in an entirely different position. The operation itself remembers the sequence. Mathematicians call this structure the dihedral group of order 10, and its key property is the one we just demonstrated. It is non-commutative. Order matters. The price is that you can no longer run the procedure in your head. You have to look it up. For every pair of moves, a table tells you where the pentagon ends up. 100 entries memorized in advance. And Verhoeff needs 3 of those tables. 1 to combine moves, 1 to twist each digit by its position, and 1 to check the final result. In 2004, the German researcher Michael Damm tightened the same idea. His approach uses the same method as Verhoeff, but requires just 1 lookup table instead of 3. Both algorithms are mathematically superior to Luhn, but neither runs on your credit card. Luhn won, and the reason is not mathematics. By 1969, the global payments industry had already adopted Luhn. IBM was using it, American Express was using it. By the time the standard that defines the structure of payment card number was first published in 1989, the Luhn check was already running everywhere. This is the true power of being the first, and it's similar to the QWERTY problem. The layout of the QWERTY keyboard was designed in the 1870s to slow down the typing, not to make it efficient. The keys were placed to prevent the hammers from colliding, a problem that doesn't exist with computers. But QWERTY was already a gold standard by the time computers became a thing. Same with the Luhn's algorithm. By the time anything better arrived, every cash register, every bank card, every payment terminal was already wired around it. The list of places Luhn now runs is enormous. Global payment networks, IMEI numbers on every mobile phone, SIM cards, national ID numbers in Canada, Israel, Sweden and South Africa, United States national provider identifier numbers, the survey codes at the bottom of McDonald's receipts and many others. And yet, for all that reach, Luhn doesn't do one thing most people assume it does. It was never about security. It's a typo detector. It exists so that when a human writes down a number on a paper slip back in the 1950s or types 1 into a phone today, the machine on the other end can tell whether the digits arrived intact. That is its entire job. And it is built on a single mathematical fact. The procedure produces a sum divisible by 10, and almost any single character corruption of the input breaks that divisibility. But the procedure itself is no secret. You can always calculate the last digit if you know the first 15. That is the story of the Luhn's algorithm. But let's pull it all together. What are the 3 things I'd like you to take away from this story? First, the Luhn algorithm is a simple and powerful tool against typos. 4 steps. Double every second digit from the right, sum any result over 9 into a single digit, add everything up and check that the result is divisible by 10. That is the whole process. It's based on elementary modular arithmetic and is a simple procedure that catches roughly 90% of common numeric transcription errors. Second, Luhn isn't security, it's validation. The algorithm is good at catching simple human mistakes like mistyping a digit or swapping 2 of them, but it's no guarantee against all mistakes. And it's not a security tool. The procedure is freely available and anyone can run it. Finally, Luhn is not the best algorithm, but it became universal. Mathematicians built stronger and cleaner versions, but Luhn's version won because it was the first one. Simplicity, multiplied by the right timing, is a very powerful mix. Try the algorithm on your own card, or as a mental exercise, find the missing last digits for this card number. Drop your answer in the comments and share your thoughts. What do you think about the Luhn algorithm and where would you like to use it? Thanks for watching, think and enjoy the beauty of mathematics. See you next time!